because he had already spent 5 more years than his classmates. Yeah, but anyway, well, his development in our office is very good, and he's actually the first one of his batch of graduate to promote as senior geotechnical engineers.
Yeah, I saw his title.
Yeah. Actually, most of the graduate of his year, I forgot which year, 2010. I forgot. Most of them actually are geotechnical engineers. He is the only one that got promoted.
Oh.
Yeah, only after 5 years service in the geo, or 5 or 6 years service. A very quick promotion.
Very quick.
Yeah, well, actually, he's very smart. And Coco Yu, the graduate I mentioned to you, she graduated from Oxford University.
Oh, Oxford.
Yeah. From Oxford. I also asked her, well, you studied the PhD for 5 years in Oxford. Why join us as graduate? She has to start it from start, from scratch, and to undergo 3 years training and then 1 year responsible post before she or he can attend the chartership exam.
Understand. So I think the time is already 32.
Okay. Yeah. Okay.
Let Dr. Elvis to take over to have a brief introduction for you.
Okay. Good afternoon, everyone. It's a great honor for us to have Engineer Professor Philip Chong today for the geotechnical talk. Engineer Professor Philip Chong is a former deputy head of the Geotechnical Engineering Office of the Hong Kong government. He has been working in the engineering field for more than 30 years and has a wide range of experience, which covers planning, management, education, research, design, and construction. He's also an adjunct professor of the Department of Earth Science of the Hong Kong University. Okay. Without further ado, please join me to welcome Professor Chong for today's lecture.
Yes, thank you, Dr. Hu. Good afternoon, all students. Actually, it's very nice to share some of my experience with you. And well, before I start off today's talk, I would like first to thank Professor Yin, Dr. Chen, and Dr. Wu for organizing this class. In the coming 2 hours, actually, I selected 2 topics, which I would like to share with you. The first topic is on the routine slope design in Hong Kong. And the second topic is about the design of excavation and lateral support. Actually, in the profession, we call this a ELS design. Okay. In fact, it is concerning about the design of retaining structures. For example, deep excavation or that such a thing. And in the first topic, about the routine slope design, in fact, there are many areas that we can talk about. But because of time, well, I particularly pick up 3 aspects, which I would like to share with you. The first one is about the factor safety in the slope design. The second one is about the estimation of design groundwater table. And the third one is about the soil node design. Now, I understand that in this course, in this subject, in lecture 3, you have been taught about the soil nails. Okay, so in my talk, I will focus on a bit on the practical aspect. And about the second topic on the design of ELS, I again pick up 3 practical aspects which I think could be useful for graduates, especially young engineers. The 3 topics is about the net water pressure estimation and the change in effective stresses because of the net water pressure distributions, and also how to define the boundary conditions, especially in the when we are using softwares nowadays. In fact, we use softwares, okay, in our routine designs, but there are many tricks, okay. If we don't specified correctly that will affect the reliability or accuracy of our results. All right, so that's the outline of my talk today. I plan to spend about 1 hour and 45 minutes on these 2 topics or 6 subtopics, and I will leave the last 15 minutes and open to all students for any questions and answers. All right, the first topic on the routine slope design. Now, before I talk about the 3 subtopics, I first list out the standards and guidance for your references, all right? So that you know that, well, after you graduate from the Polytechnic University, well, when you work in the, no matter civil or geotechnical field, okay, don't be panicked, okay? There are lots of manuals, lots of guidelines, okay, to guide you on the design. And here for the slope design, the Bible is the geotechnical manual for slopes. All right. And I'm now actually responsible for the updating of this manual, geotechnical manual for slopes. And I will spend the next 2 or 3 years' time to update the whole geotechnical manual of slopes. In Hong Kong, according to the Hong Kong law ordinance and other regulations, all slopes design must be compliant with this geotechnical manual for slopes. And if your slope is actually alongside the highways, we have also the highway slope manual. And we have also a series of geo guides, but those geo guides relevant to the slope design are listed out here, okay? Especially the geo guide 7, which is a guide to soil design and construction. And we also issue lots of technical guidance notes, which supplement the geo guides and geotechnical manual for slope. And some of the technical guidance notes or a technical circular actually replace the contents of the manual for slopes and all the geo guides. Okay, so we have lots of these geo guides. And on the surface drainage design, we also have other reference documents. Okay, so there are actually lots of documents and guidance documents in hand to facilitate or to guide you throughout the design process. Now, let's first discuss about the first subtopic that I select is on the factor safety. First of all, the factor safety of a slope, if you are engaged in a slope design, okay? Now, in the university, you are taught how to analyze the stability of a slope. Normally, okay, through the limit equilibrium approach. That is, you may use the method of slice, no matter if it's a B-shot method, Jambo's method, Morganson and Price method, etc. Okay, you can finally come up with a factor safety, which indicates the stability of a slope. And in the design, you need to compare this analysis with a requirement. What will be the required factor safety for a particular slope? Okay, now that is the minimum factor safety required, and it is stipulated or it is specified in our geotechnical manual for slope. All right, so I would like to share this with you now. But before I tell you what will be the minimum factor safety required, you need to understand the concept, and this is our slope management and engineering design, where in Hong Kong actually is based on a consequence-based system. Now, what does it mean by consequence-based system? Now, I suppose most of you have heard about the term risk, right? Risk. In Chinese, we call it 风险, right? 风险. This risk in many cases was misinterpreted by the laymen, by the media, okay, by the citizens, which equate this risk as the probability of failure of something. Now, in fact, in simple terms, this risk consists of 2 elements. One is the consequence of event that that is, if there is a landslide, there is a failure of the slope, what will be the consequence? Now, that is the consequence of event. The second element is the likelihood of occurrence. That is, how likely the slope will fail. Or in other terms, what is the probability of failure of that slope. Now, the multiplication or the product of these two terms give us the risk concept. Okay. Now, as I said, in most of the layman interpretation, they equate risk as likelihood. But in fact, in Hong Kong, in our slope management system, in our engineering design of slope, we actually base our risk analysis on consequence. That is, we are more concerned on consequence and not on the likelihood of occurrence. And hence, in our standard as set out in the geotechnical manual for slope or under the Hong Kong Ordinance, the minimum factor safety required actually depends on two consequences. One is consequence to life. In short, we call this CTL. Okay, consequence to life. And another one is based on economic consequence. Okay, we actually based on these two consequences to set up the requirements of minimum factor safety. All right, so it is a consequence-based system. So don't misunderstand the risk of a slope and equate it to the probability of failure. And here I list out actually the requirements in this table. As I said, it depends on two consequences. So it depends on your slope, whether it falls into category 1, 2, or 3 of this CTL, consequence to life, or category A, B, C of the economic consequence. Okay, I will give you examples. What are categories 1, 2, 3, or A, B, C in a minute. It actually follows a very sensible concept. That is, if your slope, if it fails, it will affect important facilities, such as schools, hospitals, buildings, BC roads, etc. Okay, then they fall into category 1. There's affecting major facilities. Okay, for intermediate facilities, there's category 2. Cat 3 belongs to those where the facilities are actually not very important, not significant. Okay, so that's the concept. And similarly for Cat A, for very significant economic loss. Okay, if the slope fails. Now, you probably, if you are actually pay attention to, you probably heard I repeat this phrase many times. If the slope fails. Now, in fact, it also comes to this. If the slope fails, that is irrespective of the failure. We are not concerning about whether the slope has a high probability or low probability of failure. We actually don't consider this. What I said is, if the slope fails, what will be the consequence? Okay, so the consequence. Now, under 10 years return period of rainfall, I will talk about this under the groundwater. Okay, under this 10-year return period of rainfall, the minimum factor safety required actually are specified within this table. So if your slope is an important slope, important in the sense that it actually, as I said, if it fails, it will affect important facilities, then your slope has to decide to have a minimum factor safety of 1.4. Okay, that is the meaning of this table. If your slope actually affects only intermediate facilities, then probably you may require only to design it up to a minimum factor safety of 1.2, etc. Okay, so that's the requirement in Hong Kong for slope design. And in the coming 2 slides, I show you examples of category 1. Now, and under CTL and also economic consequence category A. Now, the first one, now here, if you go to geotechnical guidance note 15, we list out lots of examples for 3 different categories. But for the sake of explanation here, I only pick up some examples to illustrate to you what are the important facilities under category 1 of the CTL. Okay, the first, of course, is heavily used buildings. As I said, residential buildings, schools, hotels, hospital, well, okay, they're very sensible and easily understood. Or others, which may include railway platforms, waiting areas, or road with very heavy vehicular density, traffic densities. Okay, most of the highways fall within this. Or even for lightly used building, for example, car park buildings, indoor sports hall, sewage treatment plant, a temple, church, etc. Okay, so as you can see, if your slopes actually affect these facilities or be affected by these facilities, then they fall into category 1. And another slide shows you examples of the economic consequence. That is, should the slope fail, that this will actually suffer the economic consequence in this way. That is, if the failures affecting buildings, which could cause excessive structural damage, or affecting essential services, or affecting the major roads, etc., then this fall into category A of the economic consequence. All right. So as you can see here, if, as I said, in simple terms, if your slope affect important facilities, that is Cat 1 or Cat A, then 1.4 is the minimum. Okay. So this is the first part about the practice in Hong Kong to specify the minimum factor safety of your slope. And this actually shows you an examples of the slopes. In Hong Kong, well, these wheels are actually very common. That is, we have large slopes in close vicinity of the buildings, or to major roads. Okay, so that's why, well, even though, well, some of our slopes are not really very high, especially compared with the scale in other countries or in mainland China, the slopes in Hong Kong relatively actually not very high compared with them. But because of their close proximity to the facilities, to buildings, to roadworks, okay, so a failure actually will affect the loss of lives and properties. And this is simply not acceptable. All right. And now we know, well, the categories, the concept of categories, which we use the categories, the concepts to define the minimum factor safety. Now, but there is one more aspect that we need to think about in practice. That is, should the slope fail, would the failure debris affect the facilities near slope crest and or slope toe? Now that is, even though in my slope is overlooking an important facility, for example, a multi-story building. But if the slope fails, the total amount of failure debris actually cannot reach the facilities, then why should we classify this slope as category 1? Okay, because even though the slope fails, it doesn't bring out a concrete effect, okay, or damage to the facilities, right? So it actually comes to another concept, and this concept is about the travel distance, or in other terms, how mobile the failure debris is. Okay, now it actually depends on, well, two things, which I will show you later. And one is on the type of slope, whether it is a cut slope failure or field slope failure. Okay, and the second one, it also depends on the volume of failure. As you can imagine, the larger the volume, the larger normally will be the influence zone, Okay, so it depends actually on how mobile the debris, that is on the type of slope, cut slope or field slopes, and also on the volume of failures, all right, which you will see in a minute. Now, how can we estimate the travel distance? How can we estimate this? Now, I will show you in this in the coming slide. But before that, I better explain the concept to you first. Now, we actually express the travel distance in terms of travel angle. In terms of travel angle. Okay? And I will show you how to estimate this travel angle. Okay? To see whether your slope is really belongs to a Cat 1 slope. Okay? So that your minimum factor safety is 1.4. Now, we actually give examples, okay, in the geotechnical manual of slope and WP in the technical circular. In fact, all those examples and also the table I showed you refer to the situation where the facilities lie within the expected travel distance of debris. That is, when we say this slope is Cat 1, we have an implicit assumption that we assume if the slope fails, it will affect the facility. Okay? So we will expect the facility actually lie within the expected travel distance. Okay? Now this is our implicit assumption. But in fact, if your facilities, after estimating the travel distance, lies beyond this travel distance, then your category can be downgraded by one order. Initially, after initial assessment, you assign your slope as Cat 1. But later, when you find out the facilities, in fact, lie beyond the expected travel distance, then you may downgrade your category to 2. Now, this may have a lock-on effect on the minimum factor safety required. Okay, but remember for Cat 1, it must be 1.4, the minimum factor safety. But if it is downgraded to 2, it could be 1.4 or it could be 1.2, okay, depending on the economic consequence. Now, here, I want to emphasize this term, expected travel distance, because we have another term in the third bullet point, where we call extreme travel distance. Now, we have two travel distances. One is expected travel distance. Another one is extreme travel distance. So if your facilities lie even beyond the extreme travel distance, then you can further downgrade your category to Cat 3. Okay? So your task is that once you have an initial assessment, say if it is a Cat 1 slope, so my slope has to design for at least a factor safety of 1.4. But please check the expected travel distance and extreme travel distance. Okay? Now, here in the coming few slides, I showed you how to check this. To check whether the travel distance, we actually invent a concept. We call it travel angle. This is a travel angle. What is a travel angle? A travel angle is that this is your original slope profile. Okay? Now, if this slope fails, then this will be the failure surface. And this is the failure debris. Okay? The failure surface. So what is a travel angle? Travel angle is that you join a straight line connecting the crest point of the failure surface to the distal end of the failure debris. Okay, so you have a straight line and the inclination is travel angle. All right, so this travel angle, if this is known, then it actually tells us whether the debris will hit the facilities or not. If this travel angle is known. Okay, now in reality, this travel angle actually, now let's see some of the features of this travel angle. A small travel angle means that the debris are more mobile and can travel even further. That is, the influence zone is larger. If the debris is mobile, okay, it will be reflected by small travel angle. Okay? Now, in reality, we have no way to measure this travel angle. Why? Because my slope hasn't failed. all right, or not even constructed. How do I know how it fails? Okay, I don't know what will be this failure surface. And it's difficult to draw this green line. All right, now so in reality, in practice, it is difficult to estimate this travel angle. So we borrow a concept of shadow angle. Now shadow angle is what? Is that this is my original slope profile. And this is the endpoint at the slope crest. And if I draw a straight line parallel to the travel angle, then I will see at the end of this straight line whether it will reach the facilities or not. If this red dotted line reaches the facilities, then the slope failure will affect the facilities. Okay, now because this, we can actually estimate the travel angle, as I will tell you how, based from our database of previous hundreds and thousands of landslide cases. We actually come up with some recommendations on the travel angle. All right, and you can draw a straight line here to your facilities and measure the angle and then compare with the required travel angle. You will know whether the slope failure will affect the facilities or not. Okay, so in practice, we assume this shadow angle is in fact the travel angle. All right, now, how we give recommendations on the travel angles. Now, here are some of the data points we obtained from past landslide investigations. On the vertical axis, there are travel angles. Okay, the actual travel angle. Now, we know the travel angles because the slope has already failed. We obtain this data from landslide cases. So we can measure the travel angle of each slope and also the volume of debris of each landslide. So for each landslide case, I have a point where vertical axis is the travel angle and the horizontal axis is the landslide volume. That is the volume of the debris. So each landslide will give me a point. And from this plot, we can roughly actually recognize that, well, for cut slope fell from sliding or fell by washout, or fill slope fell from liquefaction, or fill slope fell from sliding, or fill slope fell from washout, they may have different locations or positions in this graph, okay? And actually for cut slopes, there's open circles. For cut slopes, the expected travel distance. Now, remember we have two travel distances. One is the expected one, that is a nominal one. One is the extreme one, unlikely, okay, the one unlikely happen. Expected, or the lower bound one, extreme, okay? So the expected travel distance for this one, well, we take it as 35 degrees. And unlikely one, the extreme one, is about 25 degrees for cut slopes. Where for fill slopes, okay, this square and also the black circles, okay, the black circles and this squares. For fill slopes, they are more mobile, especially for fill slope fell under liquefaction. They're very mobile. So our expected travel distance is about 25 degrees for fill slopes and only 15 degrees for extreme travel distance, okay? And also, we have seen, well, it also depends on the volume, okay? And we actually, based on judgment, we choose this 300 cubic meter as a division line, all right? This what we call a relatively smaller volume, and larger than 300 is a large volume. Now, with all this in hand, we can then set up this guidance table. You can look up this table in our Geotechnical Engineering Office Technical Guidance Note 15, all right, which gives you the travel angles of your slope. And it actually consists of two parts. First one is the expected travel distance. And this second half, the lower half table, give you the extreme travel distance. All right. So for your slope, see whether your slope is a cut slope or fill slope. Okay. If you're going to design a cut slope, and now see whether your debris volume, if your slope fails, what will be the debris volume? If the debris volume is smaller than 300, then this is your expected travel distance, 35 degrees. So you can draw a 35-degree line from your slope crest to see whether it will hit the facilities. Okay? And if your debris volume is larger than 300, then you have to pick up 25 degrees, etc. And after you have checked the expected travel distance, you may then check the extreme travel distance to see whether your category can be further downgraded. All right. And again, depending on whether it is a cut slope or fill slope, depending on the volume of debris. So you can look up this table to see which number you're going to adopt in your design. Okay. Now everything seems fine. Everything seems fine. But I now know what will be my expected and extreme travel angles. But yet there is a missing data. What is this? Debris volume. In my design of the slope, of course, I know it is a cut slope or fill slope. There's no problem. But my slope has not yet failed. How do I know what will be the debris volume? That is, whether should I choose figures from this column or from the column shown blue? That is, I must have some ways to estimate the debris volume. Okay? Now, to facilitate the designers, we also go back to the data point, okay, to all data in the past. And after we have studied a lot of data, we note that if we construct a table relating the volume of the debris with the slope height, we got these numbers. And we noticed that as long as our slope height is less than 10 meters, then the volume of debris will hardly over 300. Only if my slope height larger than 10 meters, then there will be more and more cases with volume of debris larger than 300 cubic meters. So the issue of choosing which debris volume now nailed down to looking at what is my slope height. And I use this as a guidance, whether my slope is higher than 10 meters or lower than 10 meters. Okay, and I can pick up the correct columns. Okay, now these are the way we specify the minimum factor safety. Now I think you have a copy of my PowerPoint. So to test your understanding of what I have just explained to you, I actually set up this quiz. Okay, we have a cut slope with a slope height and also the clearance of the slope toe to the 6-story building. And the question is, what will be the minimum factor safety required under the current Hong Kong standard? All right. So you need to see, well, my slope is overlooking a 6-story building. So which category will it be? And hence, you look up the table, what will be the minimum factor safety? Then you have to estimate, okay, the expected travel distance and extreme travel distance, all right, to see whether we have a chance to downgrade or not. So that you can go over, the previous few slides to see whether you can come up with an answer. What will be the required factor safety? I leave it to you or for your own discussions among your classmates. Now, one word of caution. Even though in this example, you find out that you have an opportunity to downgrade your category by one order, that is from Cat 1 to Cat 2, even though after calculation, after obtaining the expected travel angles, etc., you will be given a chance to downgrade your category by one. But I have to remind you, in reality, very seldom, a designer of this case like this will downgrade simply because even though there is a clearance of this and the failed debris may not hit directly the 6-story building, but this is the lot boundary. That is, this part also belongs to the lot owner. Will the lot owner allow the very expensive and precious space to be vacated and do nothing? Will it be the case? Will the lot owner build something on this platform, for example, car park or whatever, or even a garden, okay? Whenever this is a sports area, a garden, or a car park, well, then you have no chance to downgrade your slope, all right? So in practice, we need to have other considerations apart from that. All right, this is the first part about the minimum factor safety. But before leaving this, I would like to draw your attention to some interesting features regarding the use of factor safety in slope stability analysis. Now, unfortunately, I don't have time to go over the details of these interesting features with you, but I just list out here for your own, reflections. Okay, when you have time, please think about this. But the first I would like to point out is that, do you know exactly the definition of factor safety in slope stability analysis? Okay, now this is also a question I ask the candidates who are actually applying for the Hong Kong IE chartership exam or in interview in the recruitment exercise, okay, to the graduate post in the government. Do you know the definition of factor safety in the slope stability analysis, the normal definition? Okay, now this is not the very special definition when you're using finite element method of analysis. This is the common definition when you're using the limit equilibrium method of analysis. Now, this is an important point that you need to pay attention to, because in geotechnical analysis, there comes with lots of definitions on factor safety. For example, in the second part, when I talk about the retaining wall, lateral support, and retaining structures, okay, in the deck design, what do we mean by factor safety? What do we mean by factor safety? It actually comes with many definitions of factor safety, depending on which failure mode you are designing for. For kick-out, we have factor safety defined in terms to guard against kick-out. We have factor safety to guard against the minimum embedded depth. We have factor safety to guard against the use of active and passive earth pressures, etc., etc. We have many definitions, okay, on factor safeties. So my question, in slope stability analysis, please be clear what definition actually you are using in defining this factor safety. In fact, there is one common factor definitions. The second, theoretically, according to this common definition, okay, the slope will fail, or at the start of failure, which we call incipient failure. At the start of failure, the factor safety is 1. That is, a slope, if it has a factor safety less than 1, then the slope fails. All right. But in fact, it is very common that we do some analysis on existing slopes. Now, we did lots of analysis on existing slopes to see whether they have the sufficient minimum factor safety or not. If the existing slope actually doesn't have the sufficient stability or factor safety, then we need to upgrade it, okay, up to the current standard. So we did a lot of analysis on existing slopes. And actually, we noticed that many slopes actually give a factor safety less than 1. But most of the slopes are standing there without any failure, no failure at all. So it contrasts our definition of factor safety. Okay, do you know why? Do Do you know why? In fact, there are at least 5 to 6 common reasons, okay, to explain why a factor safety of a slope is less than 1, but yet it still stands there without failure. Okay, if you are asked why, can you tell us at least 2 or 3 reasons? Okay, in fact, for undergraduates or postgraduate students, they should be able to give 5 to 6. Now, can you give us 2 or 3? This is the second point. The third one, under the limit equilibrium analysis, that is, for example, the use of the Bishop's method or Morgenstern and Price method, the factor safety is assumed to have the same value at all points on the failure surface. Now, in order to illustrate this point, I actually, before the start of today's talk, I quickly prepare one slide, which you don't have this, okay? You don't have this, but just follow my explanation. Now, under limit equilibrium method analysis, of course, you need to draw a trial failure slip surface, okay? A failure surface. And the limit equilibrium analysis actually assumes the factor safety along every point on this slip surface must be the same, okay? That is, at a particular point A, here, at a particular point A, if we adopt the normal definition that factor safety is the shear strength compared with the mobilized shear. So this will be the shear strength compared with the mobilized shear at point A, okay? Now, the mobilized shear could be different from point to point. That is the disturbing stress, represented by these red arrows, the difference from points to points along the slip surface. So mobilized shear is changing. And the shear strength, that is the black arrow, is also changing. Now, even though you assume or adopt the very simple Moore-Coulomb failure criteria, that is, this shear is given by Moore-Coulomb. That is, it is equals to C dash plus sigma dash times tangent phi dash. Even though C dash and phi dash are assumed constant throughout, your sigma dash, that is the vertical effective stress, is changing at each point, okay, along the slip surface. That is, these two terms, in fact, are changing along the slip surface. At this particular point A, I get a factor safety A. At another point here, point B, I got a shear mobilized at point B and the shear strength at point B. And at this point, I can calculate the factor safety, okay? The limit equilibrium assumes factor safety must be the same at every point along the slip surface, okay? Now, my question is, now this is actually a very fundamental assumption in limit equilibrium analysis of slopes. My question is, why? Why should we make this assumption? This is a very fundamental one. Is this assumption true or valid? Okay, now I can tell you the answer. Of course, factor safety must not be the same at each point. I can tell you right away, as actually we can see from more sophisticated analysis. For example, from definite element methods of analysis and other numerical methods of analysis, factor safeties in fact are changing from point to point. Okay, so what is the factor safety that is given? And the last one, a minimum of 1.5. Another slope give you a minimum factor safety of 2.02. Will you say that the slope with a factor safety equals to 2 has a lower probability of failure compared with the one with a factor safety equals 1.5? Will you say that? Okay. Now, I can tell you, you can't. Factor safety alone cannot give you a full picture of the probability of failure. Okay, then why on earth that we in our routine design, we only focus on factor safety, but not the probability of failure? Now, these are interesting features, okay, regarding the factor safety that, well, actually you as an undergrad or last year undergrad or as a postgrad, well, if you are interested in, can think about this. All right. Okay. Now, so much for the factor safety. Now we turn to second subtopic. Now, in the table, which I have shown you on the minimum factor safety, that is depending on the categories, okay, Cat 1, Cat 2, Cat 3, or Cat A, Cat B, Cat C. In that table, in fact, there is a note in our geotechnical manual for slopes and also in the Works Bureau Technical Circular, which supplements the part on the geotechnical manual for slopes. Now, there is a note we particularly add in. Now, what is this note? That is, in addition to the minimum factor safety of 1.4, now you know that for Cat 1 slope, you have to design minimum factor safety of 1.4, okay? On top of this, now this 1.4, as I said, is actually defined based on a 10 years return period of rainfall. On top of it, if you are designing a slope fall into category 1, you need to you need to satisfy this minimum 1.4 factor safety. But yet, there is an additional requirement that you need to check the stability has a factor safety of at least 1.1 for the predicted worst groundwater conditions. What does it mean? This 1.4 is satisfied if your analysis is based on 10-year return period of rainfall. That is, your groundwater, your design groundwater, that affects the pore water pressure, okay? The design groundwater actually is coming from 10 years return period of rainfall. Then this table is okay. If you have a Cat 1 slope, please do one more step to check even predicted worse groundwater conditions. Okay, and to make sure you still have a factor safety of 1.1. Now, here comes to a very important question. How do we specify the design groundwater level to satisfy 10 years return period or the predicted worst groundwater conditions? How do we specify this design groundwater table? And that's why here comes to my second subtopic on the design of groundwater level. Now, this slide actually serves as a very brief introduction to remind you the importance of pore water pressure in the stability of slopes. Okay, I hope, and I'm sure actually, most of you have learned the role of water pressures, especially when you learn the principle of effective stress. Okay, so that's why, because we use the effective stress in obtaining our shear strength of the soils, and that effective stress will be governed by pore water pressures, okay, significantly. So here I show you an example that in an infinite slope analysis, infinite slope means that a very long slope, okay, with constant angle, and also the failure surface actually is shallow compared with the length of the slope. Now, this is an infinite slope analysis. From an infinite slope analysis, depending on whether my soil has only cohesion, only has a friction or a C-fine soil that is with cohesion and friction. Okay, depending on whether my soil is dry, that is the groundwater level actually is located below this slip surface, or do I have a fully submerged, that is fully saturated slope, okay, with seepage, because this is a sloping ground. So when there exists water, there will be seepage. Now, here I put down some numbers and I give you the factor safety obtained. I just want to use this to illustrate to you why the water pressure is so important in the stability analysis of slopes. For a frictional soil with phi angle only, for dry slope with a slope angle of 30 degrees, the factor safety calculator is 1.21. Okay, but if this slope is filled up with water, that is the groundwater, is actually at the surface, then your factor safety is dropped to 0.54. That is more than 50% of drop in factor safety because of the rise of groundwater level. So you see how significantly the water pressure affecting our stability. Now, so this groundwater estimation, in fact, is very important in the slope stability analysis. So again, on the standard, what is the standard or requirement on groundwater level in the slope design in Hong Kong? Now, in Hong Kong, the standard actually is very simple, just one sentence, which I highlight here. Slopes in Hong Kong are designed for the groundwater conditions that would result from a 10-year return period rainfall. Now, that is the requirement on the groundwater level. Now, for most of the graduates, for most of the new designers, they don't know how to do it. How? What I need is to design groundwater level, but yet what the standard tells is that you need to design your slope to cater for a 10-year return period rainfall. Okay, now I hope you have some concepts about return period, right? 10 years return period rainfall in Cantonese 10年一遇, okay? 10 years return period. You can imagine if you have to design for 100 years return period of rainfall, the rainfall intensity will be more significant, will be larger than a 10-year return period rainfall. Okay, in Hong Kong, we need to design for 10 years return period rainfall. So how then we correlate this requirement to our design groundwater level? Now, you find it, or most of the designers find it difficult simply because in our standard, we specify the rainfall quality. We need to design for a rainfall intensity that only occurs once in 10 years as an average. Okay? So an intensity. This is the 1 in 10 years return period of rainfall. But what we need is the predicted design groundwater level. To correlate this 1 in 10 years rainfall intensity to our design groundwater level, there is a missing link. And this missing link is a groundwater model. Okay? And unfortunately, there are not many successful groundwater models available to us. And in fact, in Hong Kong and also in most of the foreign countries, people rely mainly on the piezometric reading, that is the readings from a piezometer, and then add on some empirical experience or some empirical rules or the rules of thumb, okay, to work out the design groundwater model. Now, this is very difficult. Now, the groundwater model, don't mix it up with those groundwater model we mentioned in the hydrology or in the agricultural studies. Okay, those groundwater models are meant to cover large areas, okay, regional areas, because they are looking for the source of groundwater and the recharge effect. Okay, so they're talking about very large areas. But in Hong Kong, in our design, we're talking about very, very localized area. Actually, the area where our slope is sitting. We're dealing with a slope. So we're talking about a very local area. So the groundwater used by the geologist, by the hydrologist, and also by those people working in the agriculture are not applicable to our case. In fact, in Hong Kong, we do have 3 common groundwater models used by our colleagues in the geotechnical engineering office. That is for in-house design in the government. Now, actually, we required all graduates enter into or to join our office, okay? When they are involved in the slope design, we ask them to go through these 3 groundwater models to estimate the design groundwater table. One is the model proposed by Professor Peter Lam in Hong Kong. It's called the wetting band method. Another one is proposed actually by our office earlier studies in the mid-levels in the 1980s, okay, which we call empirical extrapolation methods. And the third method is called graph method. That is a groundwater rise and fall approach method proposed by my retired colleague, Stephen Yip, in 1994. Now, nowadays, we have 3 more commonly used methods. They are rough methods, approximate methods, suffer from many limitations, okay? But yet, they are analytical methods. And I list out here the references, okay? So if you have chance to involve in a real design, then you may need to look up these 3 methods, which of course, I won't cover here because of time. But I would like to let you know that, in fact, the majority of the designers in practice, they don't use these analytical methods. They follow a rule of thumb practice. Now, what do they use in the design groundwater levels? They usually assume the design groundwater level equals to a certain percentage of the slope height, which is illustrated here. Say, for this slope design, if your piezometer gives a reading, tells you that the maximum groundwater level is well below your slope toe, okay? And yet, you, for safety's sake or conservative sake, you still to design a groundwater level up to 1/3 of the slope height, okay? This is a rule of thumb practice, certain percentage of slope height. Some people use 1/3, some people use 2/3, okay? And another empirical rules, people may add an additional water depth on top of the measured maximum piezometric level. Say, if your piezometer gives you the maximum groundwater level as shown here, then on top of this measured maximum, I add a number which ranges from 1.5 meters to 3 meters on top of it as my design groundwater levels. Now, these are empirical methods, actually very welcome by the designers in the consultants, okay, in the contractors alike. But within the GO in Hong Kong, actually we promulgate these 3 methods because they satisfy the 1 in 10 years return period rainfall. Well, but I don't have time to go over each one in details with you. But in fact, I'm planning to arrange Hong Kong IE actually a workshop on this, probably by the end of this year or next year. Well, anyway, this is the design groundwater table. Now, I would also like to draw your attention to that. In addition to the main groundwater table, we need to pay attention to the possible occurrence of purge water table. By purge water table, it means that it is not a main groundwater table, but because of the contrast in permeability of different soil strata. For example, if you have a porous materials on top of a less porous materials, then upon heavy rainfall, there may be a temporary buildup of water table, okay, because of the contrast in permeability. There will be a temporary buildup of purge water. This is what we call purge water table. So in some, actually in each stability cases, you need to consider whether your geological model will allow purge water table or not, okay? Because it also affects the factor safety calculated. Purge water table, And I would like to let you know one interesting, observation. Now, I arranged a benchmarking exercise last year. Now, what's this benchmark exercise? I actually invite the major local geotechnical consultants in Hong Kong to participate in this exercise. I prepare 3 slope cases and ask them to work out their method of slope stability analysis. That is, whether they will use Morrison and Price method, or whether they will use a Bishop's method, or whether they will use other methods, okay, apart from the limit equilibrium methods, or which softwares they are using. Are they using Oasis slopes, or are they using Slope W? Okay, what type of softwares they are using, okay, in the analysis. The second part, how do they choose the shear strength parameters? That is, for example, here I have 4 layers: residual soils, colluvium, completely decomposed volcanics, and highly decomposed volcanics. This is tough. So how to estimate the shear strength parameters, that is the C dash and phi dash of this 4 strata? Okay, how do they estimate these shear strength parameters? Of course, most of them estimate the parameters from triaxial tests, from laboratory tests, but yet for the same triaxial test results, different people will interpret different results, okay? So we know how do they interpret this. Thirdly, how do they estimate the design groundwater level? Okay, I actually organized this exercise last year, and I invite the major consultants to join, which include, for example, AECOM, Arupt, CM Wong, ESA, Fugol, Golda, Howcos, Jacobs, Lambert, Mannings, and Maiha. They are actually the main key players now in geotechnical field, okay, in Hong Kong. And I also invite 2 internal teams from GEO, one from our geotechnical projects, one from our landslip preventive measures project 2. Okay, we also invite in-house people to join this benchmark exercise. Now, there are many, many interesting findings from this benchmark exercise, okay, on slope design. But because I'm now discussing with you on the design groundwater, so I will just show you how they estimate the design groundwaters in the next 2 slides, which is interesting. Now, in one slope, this slope, where the piezometer actually shows no readings of groundwater, okay, that is the groundwater, the main groundwater is well below the slope toe. So those consultants and in-house designer, they opt to use empirical methods, okay. Now you see, most of them will choose, as I said, the 1/3 height, slope height as an empirical rule. They assume the groundwater rises up to 1/3 of the slope height. And some of them use empirical method by adding 2 meters on top of the piezometer tip. That is, we call this is the maximum groundwater level, okay? So they add 2 meters on top of it. And yet, 2 of them use one of the analytical methods, wetting band, okay, proposed by the Professor Peter Lam. And what do you notice? That, well, there actually is a large variations in the groundwater, even though when the consultants, they claim to use the 1/3 slope height, you see there are different slope groundwater profile. Okay, so this is one very interesting observations we got. This is the result of another slope. In this slope, we do have groundwater response, okay, from the piezometer. We do have the ground measure maximum or highest groundwater level. So more people will use analytical method, okay. Also, they also use the empirical one. Now, this empirical method that is here, you see, based on 1/3 to 2/3 height, but mostly they will use 2/3 height because 1/3 of the slope height will actually have a groundwater below the measure highest groundwater level. So they opt to use 2/3 or a value in between 1/3 to 2/3. And more people adopt the extrapolation method and analytical method and the graph method as well. Okay, so an interesting fact is that you can see, well, the wide range of variations from the local consultants and in-house. They are, as I said, the major key players in geotechnical design in Hong Kong. Okay, these few major consultants. This is our observations. And I would like to add some lessons to learn here. Now, in the teaching of soil mechanics in universities or geotechnical engineering subjects, foundations or other things, okay, it is all too easy to leave the students like you, even in your final years, okay, of your study, with the impression that our soil mechanics subject or geotechnical engineering subject is now an exact science, and that everything can be calculated. It's too easy to leave you have this. Especially nowadays, we have softwares, we have complicated equations, okay? It actually misleads you that, well, everything can be calculated. In pure science, a very sharp distinction. Now, this quotation, you see there's a quotation. I quote here from our father of soil mechanics, that is Karl Tasaki, in his presidential address in the first international conference by the International Society of Soil Mechanics and Foundation Engineering back to 1930 something. Our father of soil mechanics, in his presidential address, he actually voiced out this. In pure science, a very sharp distinction is made between hypotheses, theories, and laws. The difference between these three actually dependent on the weight of sustaining evidence. The more evidence we have, the higher the status we are. We have full sustaining evidence, then we say this is a law. Otherwise, this is a hypothesis. Okay? However, in our soil mechanics, in our geotechnical engineering, everything is called a theory after it appears as a paper in the journal, in a conference. And if this theory finds its way into a textbook, then many readers will consider it as a law. Okay, so please be careful and watchful about this. Don't fall into this trap that everything can be calculated and our science is an exact science. The third subtopic I would like to share with you is on soil nail design. Now, you have learned the soil nail design and analysis, I think, in this subject, right? In this course, because this is a topic of your lecture 3. And here, I just want to discuss something practical with you. Now, all the details about soil nail design in Hong Kong, no matter we are considering the initial preparations down to the detailed design and also the construction details and also the site testing, etc., can be found in GeoGuide 7. And by now, I suppose you all know what soil nails are. They are actually very simple device that, well, we simply drill a hole, okay? Drill a hole and then put a steel bar at the center of the hole and then grout it with a cement grout. And then we build a soil nail head, okay, near the slope surface. And that's it, a very simple one. Yet, it is very effective. Okay, it is very effective. Now, in the soil nail design, in fact, in design office, it actually covers a lot of things in practice. The one I suppose you learned in the university is only a very small part of it, and in many cases, the most easiest part of it. All right, here I show you a design flow chart for a cut slope design by using soil nails. you have to go through the desk studies. Okay, from the desk studies, actually you have a lot to studies, okay, in the office before you come into the detailed design. And you must, as a designer, pay visit to your site to have a look, okay, of the site where your slope is located. Okay, don't tell anyone that you have designed a slope without visiting the site. Okay, this is actually a fatal error. All right, so you have, from the site visit, I may gather lots of updated and more relevant information to supplement those information I got from the desk studies. From this desk study, nowadays we have lots of database and lots of documents actually we can actually retrieve. And also we may also from this desk study take a look of the previous ground investigation and laboratory tests in the vicinity. Then after all this, you can plan your own ground investigations and also your site-specific laboratory tests to build up your geological model and design parameters. Now, this is a very important step in the whole design process and also in our geotechnical design. The construction of a reliable geological model with reliable design parameters is a major part of the whole process. I can tell you that 9 cases out of 10 we base on the geological model to make our decision. And I can also tell you that 9 failures, 9 landslides out of 10 are coming from a poor representation of the geological models, especially a poor representation of the design groundwater level. So I cannot emphasize more on the importance of this part. So when you go into, after your graduation, when you join the industry, okay, when you have a chance to involve in any kind of geotechnical design, no matter it's an embankment, reclamation, slope, tunnels, deep excavation, foundations, okay, please make sure you got a reasonably reliable geological models and design ground parameters from normally from the laboratory and sometimes from the lab. Now, in the slope stability, from all this, you can then check out your minimum factor safety, which I have already discussed with you in my subtopic 1. Under Hong Kong standard, what is my minimum factor safety? And you can now conduct the first slope stability analysis without any soil nails to see whether this slope satisfies the minimum factor safety. Of course, in many cases, it doesn't. Okay, it doesn't. And now, this part, slope stability analysis, okay, and some part about the GI and lab test, okay, are the main ingredients you learned from the universities, okay? And actually, in the whole process, we spend lots of time on the desk studies and site visit, okay? Because they actually help us to build up these geological models. When we have some site-specific GI and lab test data, okay, we further enhance our geological models. Now, if we need to have soil nails or other things, we need to do an option analysis. How to make our slope stable to such an extent that it satisfies the minimum factor safety. Okay, that is how to make our factor safety upgrade to the minimum factor safety. Now, there are many options. Soil nails is only one of the options. You have to think about other options. For example, for slope stability, you may cut it back, that is, lower the slope angle. You may do the cutback. which is very common, actually which was very common in the 1970s and 1980s. You cut back from the slope. But nowadays, we don't recommend this method due to various reasons. Okay? Now, but this is still yet one of the options if available. Cut back. Or you can build a retaining wall at the slope toe so as to lower the slope angle. Okay? Now you have many options. You may also install ground anchors, etc. Or you may use cement soils to strengthen a field slope. You may have lots of options, and you need to analyze various options. Okay, you need to consider the economic cost. That is, which one will be more expensive, which one is more cheaper, and you need to also consider the duration. That is the time for construction. If one actually costs you 9 months and another one will take you 2 years, so which one will you opt? You need to consider any construction difficulties. You need to consider any know-how or the knowledge or the techniques available locally. You need to consider lots of things anyway. And then finally, you may come up with this saw nail design. If this is a file saw nail design, then you need to conduct, after you have designed the saw nail, you need to conduct the slope stability analysis again, okay, to see satisfy the minimum factor safety. And then you need to design for surface drainage. Okay, so you can see the whole flow chart, all right? And in fact, I think some of the materials you learn from the universities actually will enable you to kickstart of this design. And I think you probably have learned this, that is, for saw nail design, we adopt a very conservative approach that if this is the potential slip surface, we actually divide the soil slope into 2 portions. One active zone, which is colored pink here, and another one is the passive zone. Our conservative assumptions in saw nail design is that only those portions of saw nails in the passive zones are working. We neglect all the resistance from the saw nails located in the active zone. Okay, so we only calculate the strength offered by a saw nail at this portion. For this nail, only this length gives me the resistance. Okay, so we only calculate the resistance of those portions in the passive zone. And I'm not sure you have come over with this or not. I extract this from the GeoGuide 7, which shows you some of the typical failure modes. Now, we need to understand the failure modes so that we can design properly to guard against the failure mode. So that's why we need to study the failure modes. Okay, for example, the saw will flow around the saw nails, the bearing failure. So that's why we need to design the saw nail head. Okay, and there could be local failure between saw nails. All right, and this tool actually will normally be guarded against sometimes by the center spacing of the saw nails. And you need to know there could be tensile failure due to the breakage of the steel. So you need to design against the tensile failure. Or the grout and the soil interface, that is the soil and grout bonding, is not sufficient. So the whole nail will be pulled out. Okay, so we need to guard against this grout soil interface failure as well. And there could be bending and shear failure, especially at the juncture of the slip surface. Okay, and here I list out the general design considerations, now which I will not go into details with you. I just list out the considerations briefly. We need to consider stability. That is this are the stabilities. Okay, so we need to consider the stabilities. And yet, for most of the graduates, you need to learn the subsequent bullet points normally during the on-the-job training process. That is, when you really join a consultant, a contractor, or a government department, okay? When you have actually involved in the design process, then you will be heavily involved actually in other design considerations, not just the stability one. In the university, most of you will learn about this stability calculations. But in reality, in practice, we need to consider others as well, okay? Equally important. The serviceability. We need any excessive ground deformations, etc. The drainage system. We need to consider the durability, whether the soils actually surrounding the soil nail are corrosive. We need to assess the corrosiveness. And in GeoGuide 7, there is a table to assess the corrosion. If it falls into different categories of corrosion environment, we have a corresponding remedial measures, okay, to guard against these aggressive soils. So we need to consider the durability, and we need to consider the economic considerations. Now, nowadays, we don't need actually, this one actually satisfy very easily. Why in Hong Kong we so often use soil nail system? One of the reasons, because of the economic considerations, okay? Because it is actually buildable in Hong Kong. The local know-how, the technology, the skills are very, very mature. And we need also to consider any environmental impact to the surrounding, all right? And especially during the construction of the soil nails, all right? Some of our options actually, not options, some of our cases in the past, we at last dropped the option of soil nails because it induced such nuisance that cannot be, remedied. That is, we cannot actually introduce remedial measures to combat or to minimize the nuisance, especially the noise generated, okay? In some areas, it is totally not acceptable at all. So we need to consider environmental considerations. Now here, I show you examples. You don't need to be bothered by the details. I just show you example, get a feel, and that's okay. Here is a soil nail slope, okay? Two layers, a CDG, completely decomposed granite on top of the highly decomposed granite, and then overlying bedrock, all right? And now I just want to show you that now, initially, the factor safety is 1.24, and the minimum factor safety is 1.4. So we need to install soil nails. Here, we install 9 rows of soil nails. After the installation of soil nails, actually the calculated factor safety, the minimum factor safety obtained is 1.41. So it satisfies the minimum requirement. Now, and this is designed based on a groundwater table, satisfy the 1 in 10 years return period. That is satisfy our Hong Kong standard. And this is about 3 meters above the bedrock, 3 meters above the bedrock. Okay, and the nail force are here. And actually, the calculation of the nail force, in fact, are the most easiest part, as I will show you later. All right. And as I said, if this is a Cat 1 slope, you also need to check whether this soil nail slope will give you a minimum factor safety of at least 1.1 under the worst credible groundwater conditions. Now, many people interpret these worst groundwater conditions as 1 in 1,000 years return period. And the groundwater actually rises from 3 meters to 7 meters above bedrock, okay, under this very extreme groundwater condition. And yet, my design nails still give me the slope has a minimum factor safety of 1.1. That satisfies the Hong Kong standard, okay? Based on these soil nail forces. All right. So just to give you a feel how the actual design actually was carrying out, and how to calculate this nail force for this. In fact, they are actually based on the consideration of 3 parts. One part, as I said, is on the tensile strength of this steel bar. The second part is the grout and soil interface, whether this grout-soil bonding or friction is sufficient or not. Okay, this part, the soil-grout bond. And the third part, whether this grout and steel bond is sufficient or not. Otherwise, the steel bar will be pulled out, the slippage. Okay, so make sure this steel grout bond, this steel grout bond is okay. So we need to check these 3 parts. And from these 3 parts, the minimum one, actually the governing one, will tell us the soil nail capacity. All right. So to design for this 3, we need to design it for a factor safety. Now, here you see very different definition for different failure modes again. And for the tensile failure, we need to design for 1.5. For soil grout interface, depending on whether you are in the CDG or CDV, okay? So the factor safety could be 1.5 or 2. And the steel grout bond, the factor safety is 2.0. So you need to guard against these 3 failures, from which the minimum load gives you the capacity of the soil nail. Now, I will not go through the details of the design. I just list here, say the tensile failure, how to do it. The principle is very simple. I'm sure you must, and you should have no difficulties to understand it if you go through it. And the example is given. And okay, and the second part, the soil grout bond, okay, and the equation is given. Also, it is coming from a very simple physical considerations and from the effective stress considerations. And here I show you the example where in real life, in design office, how we do it using an Excel spreadsheet, okay? And also the final one, the steel grout bond, okay? The equation is given. And again, I showed you an example. As I said, I will not go into details, but in real design, you can follow this and then work out your soil nail force. That is these forces, okay? The soil nail forces. And once you have the soil nail forces, you can perform the stability analysis to see whether you attain the minimum factor safety, satisfy this. Okay, now, what is the lesson to learn here? The lesson to learn, I hope you can understand this. I hope most of the graduates can recognize and maintain good balance between education and training. Now, what does it mean by education and training? Actually, I roughly say that education means those you learn from the universities, okay? And the training, that is the one you learn from the on-the-job training, okay? And in fact, they are actually involved the basic theories and principles which you learn from the universities. And the local practice in accordance with the laid down standards and experience and the empirical methods, okay? So you have to combine these two, maintain a good balance before you can make a sensible design, all right? Blindly follow the local practice just simply implies that you are not an engineer, okay? You are not an engineer at all. You just blindly follow the book. But only understand the theories and principles cannot enable you to do an appropriate design, because our geotechnical engineering is not an exact science, and not everything can be calculated. Okay, you need to rely on experience and empirical methods. So you need to maintain a good balance between them. Okay, now I think it's almost the most of the materials I cover for the first topic. I include in this coming 4 slides just to remind you that if you use soil nails in slope design, but in field slope design. Now, what I have just mentioned to you is the saw nails in cut slopes. But if you use saw nails in field slope design, well, from theories and from practice, they are very different from cut slope design. Okay, so I don't have time to discuss with you on the theory and practice of the use of saw nails in field slope design. But just in case in your near future, you have an opportunity to design field slope using saw nails, I prepared the following 4 slides for your reference, which of course, I will not talk about them in details. These are the 3 documents, okay, nowadays available to the designers that involved in the design of loose field slopes by saw nails. I was heavily involved in the preparation of the first study, okay, and I did most of the laboratory tests for them. And now there are 2 updated documents for them, okay? So these are the references. And here I list out the design philosophies, okay, which are based on a post-liquefaction steady state and drain shear string. Now, I will not explain all this to you, okay? I suppose actually, this is actually a very strong aspect of the Hong Kong Polytechnic University, okay? Your professors and doctors actually have lots of experience on this, especially on the undrained shear string, okay? And so please understand what does it mean by liquefaction? What does it mean by steady state? What does it mean by undrained shear string? All right? And these are the design philosophies. And in fact, our goal is given by this, okay? That is the stress path is moving from point A to B, which is under drain path, and then undrained failure, okay? And we actually use this as a basis for our design, all right? So if you have learned all of this saw mechanics stuff, now it's good to test whether you understand this basic behavior, why we have a drain path horizontally, okay, move from A to B, and why the undrained stress path for a loose field materials looks like this, and then come to the steady state string, okay? So test yourself what you have learned in these 4 years regarding the concept of liquefaction, steady state, undrained shear string. And the design process is a bit different from the cut slopes because it involves the design of a grillage, okay? And we use the pressure on the grillage to design our saw nails, all right? So that's why, and that actually involves the undrained design. And after that, we then go back to the drain design. So the design of saw nails in loose field involve the drain design as well as undrained design, okay? Undrained conditions. So it is a bit difficult, I would say, than the cut slope design, all right? Just let you know that very 2 different philosophies. Okay, now, the coming 15 minutes, the last 15 minutes, I will quickly go through these topics with you on the ELS, okay, excavation and lateral support. The 3 topics. The first one, about net water pressures. Now, in saw mechanics textbooks, when you learned about the retaining wall design or lateral earth pressure theories, now you know how to calculate water pressure under static conditions. That is, there's no seepage. Under static conditions, the water pressure simply triangular, given by the unit weight of water times the water thickness, okay, water height. On the active side, on the passive side, okay, if I have 2 different groundwater levels and assume hydrostatic pressures. So right-hand side minus left-hand side, the resultant net pressure will look like this, okay? This is the net pressures acting on the retaining structures. If we assume hydrostatic pressures, okay? Now, this is a simple way to treat it, but in many cases, we don't calculate water pressure like this because we have a head difference, okay, behind the retaining wall and in front of the retaining wall. because of the water head difference, water will seep through from the right-hand side to the left-hand side through the base of the retaining wall. Okay, so that means there will be seepage in this design. And this static hydrostatic pressure, okay, will no longer work. And now this one actually is working if. Now, in fact, you can see, before I turn into the second page, now you can see that at this particular point, at the bottom or at the base of the retaining wall, the pore pressure at one side is gamma WD2. On the right-hand side, gamma WD1. They are not equal to each other, which actually violates the horizontal, not for pore water pressure, it doesn't matter. It actually violates the equilibrium conditions. Left-hand side, that is at this particular point why the pore pressure is different from the left-hand side and from the right-hand side. Okay? At a particular depth, the water pressure, all around water pressure must be the same. So it violates these equilibrium conditions as well. Now, this condition only occurs or applicable in examples as shown here. That is, if my retaining structures actually is embedded into very impervious soils, such as clay, or into bedrock, then we may assume this net hydrostatic pressure, okay, like this one. This is only applicable in practice, that if your retaining structure is embedded into something, that there is actually prevent any seepage between the right-hand side and the left-hand side. Okay. Now, when there is seepage, then I'm sorry, you cannot design according to this hydrostatic pressure. That is the blue dotted line. Instead, you need to design it, assume it is a seepage. And this is the resulting, this is the pore water pressure acting on the right-hand side, that is the active side, and the pore water pressure acting at the passive side. Okay, and the key is that the pore water pressure at the base is the same. Okay, this is the key. Now, how can we convert a hydrostatic pressure into these two diagrams? Now, there are two methods as given by Petfield and Mayer, and also given by the serial guide C5X0, now update to C760. There are two methods. I first tell you the second method, which is very simple. Once you have drawn the hydrostatic pressure, this one, the left-hand side, passive side, is unbalanced to the active side, right? You add the left-hand side and the right-hand side together and then divide it by 2. So then make them equal, divided by 2. Okay? And then you simply drop a straight line to connect them. This is the second method. Assume the average hydrostatic pressure at wall toe is the same. So you simply have this. So that's just a very, very simple method. But the first one is more logical and more actually follows the real case. It is coming from a seepage consideration from Darcy's law. That is from the hydraulic gradient point of view. Okay, and then this U, actually you can test it by yourself. If this is a hydrostatic pressure, you add them together and then divide it by 2. This is this equation. Please test this by yourself to see whether you can obtain this. But for this one, it looks complicated. Okay, and I will tell you how to do this. And this is the net pressure. Because at the bottom, these two are equal. So the net pressure at the bottom is 0. So the maximum one is somewhere here. And this maximum UC is given again by the equations, which actually you can derive it by yourself. Now, for the first method, it calls for some theories you learn from seepage, namely the Darcy's law. And how do we do it? Actually, it's simple. There's a head difference, delta H. Okay, delta H, there's a head difference. And water travels from the right-hand side along the yellow path to the left-hand side. So the total length of travel is L. That is the hydraulic gradient, is delta H over L. Okay, that gives you this uniform dissipation of the head. Okay, is delta H divided by L per meter. And so how to obtain this pressure is very simple. You first draw the hydrostatic one. This is the hydrostatic one. And then per meter, there will be a dissipation, a drop in delta H over L. Or you can multiply it by gamma W to convert it into pressure unit, okay, per meter. So per meter, there will be this dissipation. So you now have this one. Once you have one point, this is linear. So you can draw this, okay? By using this, in fact, you can derive this equation by yourself as well. For those who are good in mathematics, okay, they're actually simple algebraic manipulations. All right. So in reality, we do it either by this equation, okay, to obtain the pore water pressure, net pore water pressure, or we make use of softwares. Here I show you one of the common softwares we use is a ZipW. Okay, so here I show you the calculation. Now, this is the net water pressure if you assume static condition. Remember this? This is the net water pressure if you consider static conditions. So this is the net water pressure. But if you consider seepage, if you use the equations I give here, okay, then it will give you this black curve. So this is triangular, right? I show you that it is triangular. And if you use a software, say a ZipW, then it gives you the distribution very similar to the Petfield and Mayer. That is the equations. Okay, so this is the way we design net water pressure. Now, and a consequence to this is that there will be a reduction in pore water pressure if you consider seepage. When there is a reduction in pore water pressure, it means that there will be an increase in effective stress. Remember this? Now, that's why I discussed this second subtopics with you, change in effective stress. Remember from principle effective stress, it is coming from total stress minus pore water pressure. Now, you don't rely on the static pore water pressure. Now you use seepage to come up with your net pore water pressure. A reduction in U means an increase in effective stress. Okay, now this point is very important and sometimes forgotten by the designers. And here I show you this. If you use static pore water pressure, okay, then your effective stress will be changing like this. There's the change in effective stress behind the retaining wall. This gives you this line. And if you use a seepage condition where you have a reduction, okay, then this will be your increase in effective stress. So by assuming a static one, you will have a reduction in effective stress calculation, now which is unsafe. You underestimate your effective stress. Now, why it is unsafe? Here, I actually shows you an example. Now, in the design of a wall, if you assume seepage is not considered, then here I have this 5.4 meter. Okay, that's good. 5.4, very conservative one. And if I allow seepage, then, well, because of the reduction in pore water pressure, then my embedded depth will be shortened. So a more economical design. But the designer here forgot the increase in effective stress. If you consider the increase in effective stress, he actually comes up with this. 2.3 meter. Forgot the effect of this effective stress, 2.3 meter. Okay, now if you really believe that, well, this 2.3 meter is your final product, but without correcting for the increase in effective stress, then this is a very unsafe design. Now, I just let you know the consequence, okay? But the detailed calculation, well, you can consider it later. Now, and the last one, well, maybe I'll finish it in 5 minutes. There's the boundary conditions. Now, what's the boundary conditions? Now, I have a deep excavation like this, okay? Initially, we have the original groundwater level. Now, because of the excavation, I have to pump away the pore water pressure inside the excavation, okay? For the building of the foundations, for the construction of the basement, whatever. Now, the groundwater level is drawn down to this level. Obviously, water will seep from the left-hand side to the right-hand side, and from the right-hand side to the left-hand side, symmetrical. Okay? And because of this head difference, okay, so there will be seepage. Now, my question is, now normally you will do this kind of seepage analysis. We need to do this, okay? We need to do this to see whether the embed length is sufficient or not, to see whether there will be piping conditions, that is this quicksand condition, piping condition, to check against any kick-out failure. Now, we need to do a seepage analysis. Of course, nowadays, you will use softwares. In modeling your seepage analysis, my question is, how do you model this original groundwater level? Do you model it as a flow line or an equipotential line? Okay, I'm not sure whether you still remember your seepage analysis, the flow net. Okay, now this is a textbook type examples that you model this. This is a flow line. I'm sorry, this is an equipotential line. This is an equipotential line. Okay, so these are the flow lines. The first flow, this is first flow line. The flow lines, examples of flow lines, examples of flow lines, etc. So the dotted red curve are equipotential line. This is coming from the software. Okay, these are the flow lines. Okay, now this is one method you model this. Okay, but I can tell you that in reality, in 99% of the design of the ELS, we don't model it like this, but we model it opposite. That is, now remember this. This is the equipotential lines, but we model this as flow lines. And this is the equipotential lines. Okay, we model it differently. All right, and they actually give you very, very different results because the whole flow line actually are different. All right, so be careful how to model this, whether which one is a flow line or equipotential line. So this one, is it a flow line or equipotential? So you must need to know this kind of analysis is only true that there is a constant recharge at the upstream side. For example, a reservoir, a tank, where you have constant supply of water head. Then we can model it like this. But in reality, we have an excavation. There is no constant water supply, okay, from the top. So we cannot model it like this. Some designers make these mistakes. And I actually copied this from our GSO publication 1.0. It tells you actually what I told you, the two very different flow net. One model this as equipotential line, and one model this as flow lines. Okay? And another issue is about this extent of influence zone. In the softwares, I know the excavation depth, I know the embedment depth, but what will be this extent of influence zone? How large should I consider in a computer software? Should it be the same as the total length, total depth, or 2 times the total depth, or what? this inference zone is very important to affect our calculation of the drawdown. This drawdown is very important because this drawdown of groundwater level will cause settlement of the surface. And if we have important utilities and buildings, then they will suffer from these settlements. So it affects our calculation of settlements. It affects our distribution of net water pressures. And this will, actually, I will show you an example. And this will affect our calculation of settlements, as I said, the hydraulic stability because of change in net water pressure. It affects our adequacy of this embedded link. Okay, so how to define this is very important. Now here, I can tell you that, well, if you consider this as 45-meter length, then this will be your drawdown, you see? But if you consider a 60-meter extending, your drawdown is larger. And if you consider 90 meters, even larger, the drawdown. So it significantly affects your ground settlements calculation. So which one, or actually how large should I consider? And again, different size of inference zone affects our pore water pressure distribution magnitude. Okay, that's why I say it affects magnitude of drawdown and distribution of net water pressures. Okay, so in the subsequent slides, I actually tell you how we arrive at reasonable recommendations, which I will not go to in the details. You may read it by yourself, how by considering all this, then we think that an inference zone about 2.5 to 3 times the excavation depth will be okay. Okay, so this again illustrates to you the balance between education and training. Okay, this beautifully, I think, I hope, illustrates you need to know some knowledge about the seepage theories, about some research papers, but at the same time about the practical considerations, okay, to come up with a reasonable design guidance. All right, so thank you for your attention, and I still, I think, have 5 to 10 minutes to accept any questions that you may have. So I now turn the floor back to Dr. Wu.
Okay, thank you, Professor Chung, for your wonderful lecture. It's a very good opportunity for us to know the engineering practice for the design of slope, excavation, and lateral support in Hong Kong. I believe all of us have learned a lot in this lecture. Any questions from our students? Yes. Please feel free to ask Professor Chung.
Yes, I think you can, I don't know whether you can unmute your system or not. If you can, then you can voice it out directly, or you can put your questions in the chat room. And in fact, I also welcome any questions, not just simply limited to the materials I presented today. If you have any questions related to the career in the geotechnical field or related topics, well, I'm happy to answer. So in fact, that is the problem of using the Zoom. our experience is that. Now, again, in Hong Kong U, we also have to use the Zoom, right? In the class, the students actually are more active and more willing to ask questions. But using the Zoom, well, it's very, 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 very difficult. Yeah. And I don't know whether the same here in the Polytechnic U. Now it's time. Actually, we have almost complete all our lectures. In Hong Kong U, we have to have our exam conducted online, right? Yes, using Zoom. Yeah. That means the exam actually is a kind of open book type exam. And it's very difficult to set exam questions, okay? If students are allowed to read all the notes and books and etc. Well,
any questions?
Yeah, anyway, any questions from the students? I forgot to let you know one thing. Well, and actually, that I was also one of the graduates from the Hong Kong Polytechnic University. I joined the Polytechnic at that time, not a university. I joined Polytechnic actually in 1980s. And I, at that time, studied structural engineering. So my first chartership actually was a charter structural engineers. And my second chartership is a civil engineers. And my third one is a geotechnical engineer. And in fact, I studied structural engineering, a high diploma in the Polytechnic. I graduated in around 1984. And after that, I continued my study in Hong Kong U and later in the Imperial College and et cetera, et cetera. So actually, I'm actually very happy to share my views actually with my師兄弟妹, actually 師弟 and 師妹, right? But so any questions you would like to ask?
Maybe I ask one question. Oh, there's one question.
There's one question.
Yeah.
Yeah. Let me see. SIP page is something I overlooked during my design project. So maybe an off topic. It doesn't matter. May I ask, what can engineers do to deal with the potential slope stability problem due to climate change? It's good. Climate change. That's good. Now, actually, before I answer this, I can tell you something. But in fact, in the past about 10 years or so, I actually was the guy in the geotechnical engineering office in charge of the climate change event. And because of that, I gave lectures in the United Nations at Switzerland to introduce all the audience coming from different countries, how Hong Kong tackled the climate change issues in the slope management system, in the Hong Kong slope safety system. And in fact, in the climate change issues, we have done many things regarding the slope management and engineering. Now, we're not just confined to slope design, not just the slope engineering, but some bigger perspective, some wider perspective. We have to consider the slope management system, because as a controlling office, a department in the government, we take care of all the slopes in Hong Kong. So we are not just concerned about a single slope design, but all the slope issues in Hong Kong. So we have many aspects, to combat on this. Now, first one, we actually did what we call a pressure test. Okay, what do we mean by pressure test? That is, I don't know whether you remember or not. In 2008, there was a very severe rainstorm in Hong Kong. Okay, in 2008, and that severe rainstorm hit Lantau Island, which caused more than 2,400 landslides in a single day. But most of them are natural hillside failures. But luckily, because the rain actually fall onto the Lantau Island, which are mostly are country parks, it just only stopped the damage the village, the Tai O. Okay, and we did a test. We transposed the rainstorm of the 2008 and put that rainstorm to the Hong Kong Island and see what happens. And we did that analysis. And it tells us that, well, more than thousands of man-made slopes will fail because of that rainstorm in Hong Kong Island. Okay, so we know the situation. And we even do an even more severe scenario. There is a typhoon called Moraca, that attacks Taiwan, that kills a whole village and kills many, many people, the Moraca. And we transpose Moraca to Hong Kong and see what happens. And more than 20,000 of landslides occur that actually jeopardize all the systems in Hong Kong. So slope engineering actually can do nothing under this scenario. All right. So we have first do this kind of analysis to see where we are. And secondly, and we try to develop some resilience measures and some adaptive measures. Now, we have 3 types of measures to combat climate change: mitigations, adaptations, and resilience measures. Okay. In slope management and system and engineering, very seldom we can use mitigations. That is direct reduction of carbon dioxide emission. Now, there's very little we can do. At most we can do is we don't use cement in our concrete. We use more other materials such as GGBS or other fuel, okay, PFA, etc. Because cement is the major source of emitting carbon dioxide. Okay, so but that's very little we can do. So we don't focus on mitigation, but yet we focus on adaptation and resilience. On this adaptation, we actually implement and upgrade our landslip preventive measure system, which the Legislative Council give us 1 billion Hong Kong dollar 1 year to tackle this. We spend half of the resources on natural hillside and half of the resources on man-made slopes. And we also update and upgrade all the slope maintenance measures, okay, on this. And we also, because of the prediction of the rainfall down to the end of this century, we upgrade our design guidelines on the drainage design, okay, for slopes, for the groundwater design for slopes. And these are all adaptation measures. And on top of it, we have resilience measures. We upgrade our education system, the public education. We tell the general public to do this together with us. We tell them there is no zero risk on slope stability and landslide in Hong Kong and in the world, no zero risk. So the public has to know what to do during heavy rainstorm and to observe the precautionary measures during the landslip warning signal is enforced. Okay, so all this, we hope we can minimize the effects and to build the resilience of our city, okay, due to the effect of the climate change. I hope this will give you some ideas what we have done on this, okay? And I can see there is another question in the chat room about the uplift pressure affect the foundation of the slope and how uplift pressure affect the foundation or slope structure and how to define it. Now, the uplift pressure on the foundation is clear. Okay, we know about this, but this is outside the scope of what I discussed today. Okay, for slope, it is very seldom we have uplift pressure on slopes. I actually can't imagine how can we have uplift pressures on a slope. Okay, it just rarely occur. Now, uplift pressure on foundation, it is common. Uplift pressure on slope, this is not common, very rare. All right. So what I can think of in this moment is that in the field slope design, we do have this analysis in the field slope design. Now, if I can go back to one slide, when that I talk about the field slope design, this is a flow chart for field slope design using soil nails. In fact, we use undrained design to design the soil nail force. And what we design is to base on the earth pressure exert on the grillage to be resisted by the soil nail. That is, for a field slope design upgraded with soil nails, we need to build grillage. The grillage, I hope you understand what it is from the structural engineering. It is actually a framework or a grid of RC beams. Okay, that is on the slope surface. We build a grid or a framework of RC beams vertically and horizontally, which covers 50% of the slope surface. That is, we have a concrete hard surface, a courage beam. And the saw nails, actually, if we install into the field slope, will exert pressures on this courage. And hence, there is an earth pressure acting on top of the courage. Now, our finite element analysis shows that near the slope toe, there will be uplifting forces on the courage. And that's why in a field slope design using saw nails, the saw nails are not arranged like this. Now, you see, this is our common arrangement of the saw nails, inclined at an angle about 15 degrees to the horizontal, right? This is our saw nails in proper design in cut slope. But in field slopes, we don't do this. Suppose this is a field slope, okay? Let me turn this. Suppose this is a field slope. On the upper part of the field slopes, we have the saw nail arranged like this, okay, similar. But at the bottom part, the saw nail is more subvertical. So we have a hybrid design of saw nails. Why it is subvertical? Because we have a courage system on top, and there will be uplifting pressure near the slope toe. So we need these saw nails to nail it down to actually guard against these uplifting pressures. Okay, so that is the case that I can think of in the moment about that. Otherwise, well, there's very little uplifting pressures resulting from the groundwater. Okay, so I think I have answered these questions. So are there any more questions? Well, it's almost 6:35. Okay. So if no more questions, so I think I will hand it back to Dr. Wu to have a closure.
Okay. Thank you very much, Professor Chung, for your very wonderful lecture and also for your detailed explanation to our students. And also, if you have any further question, you can also send us email and we will try to explain you in next week's tutorial or lecture. And also, thank you very much, Professor Chung, and looking forward to meeting you in the near future.
Yeah, thank you very much. Okay, then see you then.
See you.
Okay, bye-bye.
Bye-bye.